How's it going? We've got this one last class, and we have a wonderful guest speaker here for us, Derrik, who's going to be telling us about Magic the Gathering Arena and use of compilation technology in it. One quick announcement before we get started. Andy has a nice stack of 5x8 index cards if you need those for the exam. The homework solutions I do not have with me right now, but we will have them at the review next week. And all of those, along with the homework 4 solutions, will be available outside my door starting on Monday when I get in and get those all printed and posted. So please let us know if you have any questions or need any help with exam prep. Otherwise, let's give a quick round of applause to welcome Derrik here.
Okay, is audio good? Cool. Hello, my name is Derrik Petrin. I am a software engineer at Wizards of the Coast. I work on Magic the Gathering Arena, and I'm going to talk to you about a very weird compiler that takes natural language and produces code. I've also taken this class before, the PMP version of it. I believe you guys are working on code gen right now, maybe last minute. I hope you're having fun. That was my favorite part of the project. Here's what we're going to do. I'm going to give you a bit of background on Magic, because I'm not assuming that everyone knows how to play. Who has played Magic? Okay, a good number. We're going to talk about the source language, which is Magic card text, the target language, which is something called clips, our intermediate representation, which is this thing called ambiguity-free encoded rules text. It's a very specialized domain-specific representation. Code gen for getting from AFERT to clips. Semantic analysis for getting from concrete syntax trees to the AFERT. And parsing for getting from the card text to the concrete syntax trees. And here's a kind of another way to look at the system. Yes?
Sorry, what is clips?
So we'll get to clips in a second, but it is an expert system language. It's a type of rule-based programming. The acronym stands for C Language Integrated Production System, and you can just think of it as clips. So again, source language, card text, parse it into syntax trees, semantic analysis into AFERT, and then code gen into clips. So Magic the Gathering is a trading card game that was initially published by Wizards of the Coast over 30 years ago in 1993. At this point, we've published over 30,000 unique cards. And last year, we published around 2,000 cards just in the past year. Magic the Gathering Arena was released in 2019. It's a digital implementation of Magic the Gathering. And one of the big constraints for Arena is the fact that it started almost 30 years after Magic the Gathering was first published. So there's a huge backlog of existing cards to try to support. Now, to get started, we can look at the comprehensive rules, except there's a little problem. There's a lot of them, so I'm going to give an abridged version. In a game of Magic, players make a deck of cards called a library. These are the two players. This is a view of Arena. So here's the library. Players draw cards from their library into their hand. They play resources like lands, which they can use to pay for costs. They summon creatures and other objects like artifacts. These end up in a zone that's called the battlefield, which is where objects that stick around for multiple turns end up. They'll cast spells that have effects on the game. They'll attack each other with their creatures to try to reduce each other's life total. When creatures die and when spells finish resolving, they go to a discard pile called the graveyard. And some things can die in extra special ways that send them to this other zone called exile. And we're not going to look at any of the other rules, but we're going to look at this one interesting rule, which says that whenever a card's text directly contradicts these rules, the card takes precedence. So that's kind of a hint at how important the text on the cards is. And here's a really extreme example of this rule in action. When you have this creature, you can't lose the game and your opponents can't win the game. So that directly contradicts a lot of rules. It overrides them. And of course, you want to kill this creature so that you can actually defeat your opponent. So now let's talk a little bit about our source language, which is Magic card text. We're at this point. Here's an example card. We're going to use this as our running example. It's not the simplest card. It's also not the most complex card, just a little enough to be interesting. This spell, when you cast it, it says to destroy all creatures. You gain 1 life for each creature destroyed this way. That is the rule text on the card. Ignore everything else on the card. It doesn't matter for what we're talking about. All we care about is the rule text. Let's look at what this spell looks like when it resolves. Pay for it, destroy creatures, goes to the graveyard, life total increases. Let's look at that one more time a little bit more slowly. Whoop. Here, okay. So again, we pay for the costs, then it gets to actually resolve. You'll see creatures getting blasted away, they disappear into the graveyard, and then because 3 creatures were destroyed, the life total will increase. Costs, destruction, life gain. Next slide. There we go. Okay, so we're going to do a couple stills again to repeat. Paying costs, we're not going to worry about that. That's an earlier step in casting a spell. We care about the resolving part, where we actually get to do the things the spell does. So the first thing is destroying all creatures, specifically these 3 bears. Think about how we would need to encode this in code logic. We need to destroy just creatures and not anything else. So we need to be able to specify which objects on this screen we're affecting. Not the lands, not the artifacts. We aren't destroying the players. We aren't destroying cards in the hand. So if we had a creature card in a player's hand, that also wouldn't get destroyed. We're not destroying things in the library. And then the second step, again, gaining life that's tied to what happened in that first step, specifically 3 life. Some other things that we need to keep in mind as we're writing the code for this is what does it mean to destroy something? In this case, that means to transfer these objects from the battlefield zone to the graveyard zone. And when exactly do we need to execute the logic for this card? So you might think that the code for the card somehow lives inside the object in the game, and when you move that object out, the code that's hiding inside the card emerges and does its thing. But what we instead use is something more like an event-based system that knows the rules for all of the different cards, and when spells are resolving, that event-based system will look at the game state and be like, is it this spell, is it this spell, is it this spell? No, it's fumigate. And which part of that spell are we doing? Are we doing the first step, the destroy all creatures step, or are we doing the second step, the life gain step? So we need to be able to manage that timing as well. So the important parts of the magic text are what is happening, to which objects, and when is it happening. Here I'm going to show you some examples of more difficult text to handle. So don't try to understand what's in this. The important thing is that there's a lot. There's a whole bunch of different types of control flow happening, and we need to be able to write code for this. Here's an example of a card that has some ambiguity in its meaning. The word we're worried about is it. We need to figure out what is it referring to. Semantically, we know that it's referring to a creature you control, but that's not obvious from the grammar. Here's a card that shows a tricky syntax problem. The tricky thing is this prepositional phrase, with flying. What part of the sentence is with flying modifying? Is it modifying just creature so that you can only destroy creatures with flying, but then you can destroy artifacts or enchantments of any kind? That is the correct interpretation, but grammatically, it would also be correct for it to apply to artifacts and enchantments too. It's just that we know semantically as Magic players, enchantments don't have flying, usually. But there's one other grammatically correct way to interpret this that's semantically wrong, that's very silly, which is destroy those things using some abstract concept of flying as a weapon. Destroy with flying, using flying. So these are some of the problems we have to deal with. Here's a card that has both of these problems. So look at just this top paragraph. Whole bunch of examples of those words that are referring to things earlier in the card, and we need to resolve all of these to the correct reference. And then there's this with a silver counter. Are we using a silver counter to exile things? Are we exiling them and then putting a counter on them in exile? Or are we looking for a thing that already has a silver counter and exiling that? Questions about this weird source language?
How do you handle the card odds that you need for the cards that overrule rules in the kind of set of all rules that exist?
Okay, so the question is how we handle cards that overrule the general rules of Magic. And it depends on the effect they're having, but that will kind of be handled by Clips. Clips adjudicates the rules of the game. And so as Clips is evaluating which rules apply, if there's a rule that contradicts the core game rules, that rule will get a chance to have its effects and interact with the other systems.
How are the rules encoded? Are you also applying a similar kind of compiling to the rules as well?
Oh, the comprehensive rules, the core game rules. So some parts of the rules are encoded in kind of generic Clips rules that cover generic behaviors, but also the overall architecture of the game is a big nested set of state machines that manage the flow of the turns. There's a whole different subsystem for managing the flow of combat and legality of combat. So the answer is a whole bunch of different systems. The Clip system is primarily made for handling the text on cards, which is has all of this ad hoc special ways that it can modify the game beyond the base rules.
When new cards are being created, are they written with this architecture in mind?
Great question. Sort of. Generally, the game designers are not thinking about the digital implementation at first, but later on in the review process, as they have multiple stages of review. They try to balance the mechanics. They look at how cohesive the set is. And one of the review stages is they talk to my team, the rule engine team, and ask for feedback we might have on concerns for cards that one thing we might catch is the words that they are templating out don't actually quite technically do what they intend. And because we are really pedantic on my team and focusing on like precisely what's going on, there's some things that we catch that they might miss. So there is a feedback loop there that happens, but generally we are beholden to them. Ultimately, what they put as text on cards, it's our job to make it work. Okay, so now we're going to talk about the target language, which is Clips. Clips is a rule-based programming language. That's a paradigm you're probably not familiar with. You can think of it kind of like event-based programming. It was designed for building expert systems. It was developed by NASA in the 80s and 90s, and it's now open source. And we have our own re-implementation of Clips because we needed some different performance characteristics from it. But let's talk a little bit about an expert system. This is an older, more traditional approach to AI systems. In an expert system, you have a database of facts and a collection of rules that domain experts have written that determine how you derive new facts from your existing facts. Then an expert-based system, especially a rule-based system, has an inference engine that takes the facts and the rules and determines which rules match the current facts, and then in what order to process the actions that the rules specify to update the database. And then the inference engine will keep iterating until things settle out. And so that's the core loop of the rule-based system. If you're interested in rule-based programming and want to learn more, there's a fun tutorial you can find online for it. And I'm going to give you kind of a rough sketch of how this logic of a Eclipse rule works. This is a declarative style of programming. You can think of it as like a database query, where on the upper part of the rule, we have a bunch of constraints that are trying to match a set of objects, perform some sort of database query. And on the bottom, we have an action that we're going to take for every object that matches. This is Teddy. We're trying to determine, should we be feeding Teddy? We have a rule that matches dog objects, but specifically ones that are hungry. We use this question mark syntax for variables. And so we're matching the name, and then we're reusing the name in the action that we're taking. So that's how we match the query with how we modify the state of the game, or in this case, the state of the dog. We also have a variable matching the owner, and you see in this next constraint, that same variable is reappearing. And so this is operating like a database join to show that these two constraints need to be constrained together. We also, again, have another variable, favorite food. And you see we're using it down here in this test, which isn't querying for objects, but is instead writing a more complex constraint on other objects. And it's jointly using this contents variable to check whether favorite food is in the pantry. Here's another dog. His name's Toast. What happens when we try to apply this rule is if only Teddy's hungry, the rule will fire once. It'll feed Teddy. If both dogs match, it's not that the rule will fire and feed both at once. The inference engine decides which one to feed first, and it's kind of arbitrary. So what does this have to do with magic? Well, what we're going to do is we're going to write one rule for each of the actions we're taking. So one rule for destroy all creatures and one rule for you gain 1 life, blah, blah, blah. This is what the rule looks like for destroy all creatures. There's a bunch of boilerplate, so we're going to simplify it in a second. The what happens, the action, is down here. Here we have some constraints for which objects. Specifically, we're looking at how to define creatures, how to query for creatures. And then there's a bunch of boilerplate that's managing the timing. Are we resolving specifically this spell as opposed to a different spell? Are we looking at the first step in the spell as opposed to the second step? So here's kind of a simplified version that I've stripped out the timing boilerplate. And we see that's how we're defining that verb destroy. We're tying it to a card object that we've queried in the game state. And we have this joined constraint to state that this card object needs to be on the battlefield as opposed to in the library. And we have this test to check that this card type, which is a list, because cards can have multiple types, that it contains creature. And one thing to note is this rule is not going to fire once and destroy all creatures. It's going to create a create destroy permanent effect for each individual creature one at a time. Here's the rule for the second effect. It's more complicated. We can kind of just skip over it and just know that U is being matched on the upper part, and somehow we're creating life gain, and this big blob is corresponding to each creature destroyed this way. But before I go on, we should talk about why are we doing this with a compiler? Why don't we just handwrite the rules for the cards? That was just 2 sentences, 2 rules. We have a bunch of engineers. We'll just handwrite the code. There are other digital trading card games where this is how they approach it. One of the reasons we don't do it this way is because the game engine is not what defines correctness of the cards. It's the game designers, like we talked about before. So we need to match the meaning of the rules according to this paper physical game that exists as primary to the digital game. But another big reason is scale. So let's say we have 4 engineers, and they can write the code and the tests for about 500 cards in a year. Is that enough? Well, we said earlier that there were about 2,000 cards last year, so we need up to 4 times as many engineers to handle that many cards. But we also have a huge backlog. We have tens of thousands of cards that already existed, and we want to be able to support at least some subset of those. And what if we need to refactor some of our code? The problem gets bigger. We have over 6 million lines of generated code of Clips rules at this point. And so the scaling problem really just blows up. And so we use a compiler to make this manageable. Instead, we have a dozen engineers who work on a ridiculously complex compiler, but that's more tractable. OK, so questions about Clips, this weird rule-based programming system. Yes?
Does the test just does it just return if there's no object in the database that constrains the rules, or what happens?
Yeah, so the question is, what happens if there are no objects that match the constraints? Does the action in the rule fire? And the answer is no. The action fires once for each way that the objects can match.
So yeah, another follow-up. So is this kind of like almost like a testing framework? Like, is the test kind of like an assert?
I wouldn't think of it as like the action that happens at the end is, I mean, the conditions are trying to match a state. And so if you're writing asserts that are querying for, it depends on the framework you're using, but you could have a test framework that queries game state. But this is much more like an event-based system rather than an assertion framework.
Was there any doubt in your mind about the choice of writing the compiler being the correct one versus just like hiring a bunch of people to write the code for all the cards?
So the question is, was there doubt in my mind about hiring, doing a compiler versus hiring a bunch of engineers? And the answer is not in my mind. I joined this team 3 years ago. These design decisions were made well before me. But I don't think that you, scale-wise, we're a couple orders of magnitude beyond where that would make sense.
How do you test that the card, like if the cards are compiled into like their functionality, how do you actually, are you also compiling tests to like?
Yeah, how do we test this? OK, so we have a whole regression test framework that interacts with the game server in the same way that a game client does with a bunch of messages. But we have a suite of kind of higher level helper methods that let us basically write out a scripted game. And so we write a scripted game to set up a particular state we're interested in, to test some particular card functionality, and then we assert that the result state after we take an action is what we want. So we have a completely different framework for testing that's operating at a much higher level.
So does that have to be done like manually for each card then?
Yes, yeah. We write these tests, and we do it for, so rule of thumb, about 80% of the cards in a new set will work right out of the box. We have QA that checks that not only does it compile into something, but that something is correct. But we also, every card that requires changes to the compiler, we do write tests for. And that actually is a pretty time-intensive process. And there are people on our team who are like former Magic judges who like really, really know the rules, and so we'll consult with them to make sure that we're handling all the edge cases we should during our code reviews.
In the destroyable creatures example you gave, it had sort of interweave between who does it happen to and when. Mm-hmm. Does that get more complicated than sort of every other alternating?
Yes, that big finale of promise card with the gigantic paragraph of text has a much more complex flow of logic. And the way that we coordinate which rules are firing in a multi-step process like that is more complicated. We kind of have an assembly sort of language that we run using Clips rules in a complicated way that has registers and opcodes, but we're not going to talk about that at all. Okay, I think I should keep going because this is a compilers class and we should talk about some of the compilatory things like our intermediate representation. So here, mysterious syntax tree looking thing. Our intermediate representation needs to abstractly capture these parts of the text. So we can start out by trying to break out the control flow. In this case, it's just a sequence of 2 statements, pseudo Java syntax here showing these 2 statements, but it could be a much more complex set of control flow. And we can create AST-style nodes, like the sequence node, that represent the control flow. Fortunately, Magic Card text is very regular and templated. The game designers follow specific ways for stating different kinds of control flow. So in our grammar at a high level, at the higher syntax sentence structure level, we can match on those kinds of regular templates of language to know what control flow we're matching here. But then we have these boxes of just the meaning of destroy and the meaning of gain. And we need to put some more precise meaning into these boxes. So what we're going to do is use a technique, an approach from linguistics called frame semantics. The idea behind frame semantics is, let's say we have a scenario. I am buying a banana from a banana stand. I'm buying it for $10. We can consider this whole scenario a semantic frame, and the frame is the purchase frame. So this is kind of the abstract idea of a commercial transaction. And the frame has semantic roles or slots in it that different participants in this scenario consistently play. And you can't really understand the meaning of the buyer role and the word buyer without also the meaning of the seller. Like it's semantically meaningless to try to explain to someone what is a buyer without also talking about who they're buying from and the good that they're buying and the currency they're using. So there's this kind of bundle of words that only have meaning collectively. So that's the core idea behind a semantic frame. So we'll use semantic frames to provide meaning for our verb phrases. If we look at destroy, we have one slot. We call it the recipient, and it is the thing that is receiving the destruction. So it's all creatures. Gain is a little bit more interesting. We have a recipient, you, what's receiving the thing that's being gained. We have gained, which is the thing that is being gained. And we have an enumerator, which says how many times that thing is being gained. And what you'll notice is that all of these slots are roughly corresponding to noun phrases. So we're not quite done here yet because we need to actually provide meaning to what these slots are referring to. We need to define the meaning of a noun phrase as a set of objects. So what we're going to do is we're going to appeal to first-order logic and define predicates that are true for precisely the set of objects that we care about. In this case, this exists expression is looking for something that is a card. Its zone ID matches the ID of a battlefield. And this member predicate is also true, that the creature card type is part of the object's card types. And you can also, in more mathy notation, look at it as an exists expression like this. Similarly, we need to define what the heck destroy is. And so we call the kind of meaning of the verb, the action that you're taking, a theme. And we represent it as some abstract effect definition, a game effect. In this case, it's a destroy permanent game effect. Permanent is magic jargon for all of those things that are on the battlefield that stick around. And then it has additional arguments. you see also that the theme is tied to one of the slots via the variable. So then, given first-order logic expressions that define the sets of objects that we care about, and these frames that describe different verbs that tell you what to do to the objects, and then these high-level control flow nodes, we have the abstract meaning that we were looking for. We have what happens with the frames, to which objects, and then when it is happening. Okay, questions about our intermediate representation? Cool. Oh, yes.
You guys just like parse word by word with your own I don't know, like do you guys have your own like hand-coded parser for all these words that appear in Magic to parse?
It is not a hand-coded parser. It is, we use a grammar and we use a parser generator, which should sound familiar from what you guys did. And we'll get to that depending on my timing. Yes?
Very briefly, the previous example, what was enumerator referring to?
So enumerator is referring to, yeah, enumerator is tough because it's a bit of a more abstract concept. Where are you? Slide. But yes, it's referring to this part, each creature destroyed this way. Or the for is kind of included in there. Enumerator it's not a noun phrase in this case, it's a prepositional phrase. But yes, that's what it's referring to. And the enumerator is what gets turned into that really big blob we saw on that rule before, that kind of more complex expression. Any other questions? Nope? Okay, great. So now we're going to look at, very briefly, code gen, how we get from this abstract representation to our target language. We do a lot of work to get into this abstract representation, and what that gets us is code gen's somewhat straightforward. If we look at the theme, which is the definition of that verb, that action, it pretty much lines up exactly with the action in the rule. Mapping the slots takes a bit more work because different parts map in different ways. But for the most part, this is regularized, and we have a bit of code that handles how to map logic expressions into clips, patterns, and constraints. And we never touch that code because it just works. But you can see that type is being turned into this is-a part, this class constraint. This constraint is getting turned directly into like a query on a field value. And then because we need this value for this membership test, we also query it out. And then this expression becomes a test as opposed to just a plain field in the card query. Questions on code gen? I know that part was really brief. All right, so now let's look at how we get from syntax trees to this abstract representation. So not quite parsing yet. We've already parsed and got a concrete tree. Now we need to figure out how to turn that into this abstract representation. So this is unlike, so a lot of compilers, they're structured. You've got your front end, it does parsing. You probably have a library that does it. You have your back end that does code gen, it's pretty templated. Then you have your middle end that's optimizations, and that's where a lot of the complex code of your compiler lives. In our case, all of the work really is in the semantic analysis, in taking that concrete syntax tree and turning it into the AFERT, because there's a lot of ambiguity in natural text that we need to resolve as we're translating from the grammar into the semantics. And that's where almost all of our time is spent, is resolving issues there. But we're going to kind of look at the high-level way it goes when there's no ambiguity. So here's the concrete syntax tree. There's a lot of detail here. Here's a little legend for some of these abbreviations. We have verb phrases, noun phrases, prepositional phrases. But the thing, and then also notice these numbered levels. 0, 1, 2, 3, 4 noun phrases. Same thing with verb phrases. We use those levels as a precedence system. So for nouns, we're going to combine adjectives onto our noun phrases at one level. We're going to combine prepositional phrases at another level. With verbs, we add the objects at one level, the subjects at another level. So don't worry too much about those levels. Just know it's precedence. So how do we turn this into that? Well, as we're parsing, once we're getting up at the high-level syntax structure, we start labeling with our parser our nodes with classes. The classes are indicating the control flow. So in order, as we're traversing down our tree, trying to build our AFERT tree, we know to create a sequence node because our parser told us this is a sequence node. The more interesting stuff is with the verbs. So when we hit a verb phrase, we know we need to create a frame, but we need to figure out which frame. And it turns out we have this handy head label on our verb phrase, which tells us which frame to use. And that head label is coming all the way from the way we've defined our lexeme for the verb destroy, the word destroy. We label it with the head destroy. And then the syntax productions propagate that all the way up to the higher level verb phrase. Similarly with gain, the verb gain has the head gain, and that gets propagated all the way up. But we still need to know what logic expressions we're sticking in for the nouns. And so the way that we do that is the noun phrases also have logic expressions that they're labeled with, that the parser builds as it goes. But we need to know which noun phrase in this tree corresponds to the recipient. So when we define our frame, we indicate which grammatical role these are playing. So in the case of destroy, the recipient is playing the grammatical role of an object. So as we're crawling down and we hit our destroy verb node, we then know, as we continue to recurse, that we're expecting to find a noun phrase in the object position, and we're going to take the logic out of that and stick it into the slot for recipient. However, for gain, in this case, the recipient is playing the subject role. So the semantic roles don't match up to the grammatical roles. They can be different for different verbs. Instead, the object is being put into the gain slot. And then the enumerator, instead of looking for an object or a subject in the kind of verb terminology, we're looking for a node that has a particular head related to the preposition that we're using, which is for. Let's look at what the semantics, those logic expressions look like in our nodes on our syntax trees. So once again, we're using these labels on our nodes. They look like this. And if we compare it to our first order logic expression, it's identical except for a change in variable name and this /x. The /x is just a shorthand for representing a lambda and then an x. So this is a lambda expression. So we can represent in more mathy notation, again, they're the same expressions except one is bound with an existential quantifier, purely first order logic, and the other is bound with a lambda expression. The reason that we have these as lambda expressions is we want them to be functions so that we can compose them together. And we'll look a little bit more into that as we look at what we're doing when we're actually parsing. But first, any more questions about this mapping from the syntax tree to the abstract, the AFERT? Yes?
So it seems like a pretty big pain point, this mapping from concrete to abstract. Now that you guys have done it so much, have you ever thought about approaching it with a graph-based neural network where you go from concrete and you sort of learn the semantics of the concrete to go to abstract rather than coding all these rules?
That is a good question. Our architecture is very established at this point. So if we were to insert a neural net at some point, we would have to find ways to integrate it. and that would be pretty challenging. But also, in some ways, the mapping from the syntax to the verbs, we don't need to, we can define a frame object that lets us, in a pretty abstract, reliable way, indicate like the roles of the slots that are playing. And then the parsing code that does the translation takes that as an input and can then do all of the hard work that we've already done for how to traverse the trees automatically. So yes, probably possible. Would it be worth it for us to do it at this point? Probably not. Yes?
Isn't there also the issue that like there's not really like that many magic cards, but also like there's quite a large variety of like effects that happen, and like also do effects happen all the time too. So like I don't know if like I would have too much faith in like a neural network being able to sufficiently learn that type of thing.
Right. Yes. So there are multiple reasons why we wouldn't use a language model to read the card text and directly produce code. One is language models have correctness problems and determinism problems, and we need both of those things. Neural nets also were not, language models were not useful at the point when this project was started, so it wasn't even an option. But like you said, there's a lot of variation in the potential effects that are produced. Game designers are coming up with new effects as they're going, and so that's not in the training data. So it would be hard to use language models in a way that would be maintainable in any sort of way. All right, let's look a little bit more at parsing. We're only going to look at one part, which is, we're going to talk a bit about how we're doing the parsing. We're using a library called NLTK. It's an older style of NLP library that's focused on grammar-based analysis. We use a feature-based grammar. I'm not going to get too much into what that is, but that's where those labels are coming from. Our syntax nodes aren't just atomic nodes. They have dictionaries of values that they carry around. Feature-based grammars help you deal with all of the combinatorial ways that natural language relates. You have to have agreement between your nouns and your verbs, your subject and your verbs. You have to have agreement in the number for the verb and the noun, and also the person. You have to keep track of whether nouns are plural or not. And if you do that purely with syntax nodes, you'll get a combinatorial explosion. So a feature-based grammar is a way to compress all of that complexity. We use a chart parser. One thing that a chart parser gets you is it produces multiple syntax trees for a given sentence. You guys were dealing with an unambiguous grammar and fighting to get your grammar to be unambiguous. We can't do that. The grammar is ambiguous. We have to deal with it. And we deal with it by parsing every possible grammatical tree and then finding which ones to prune away. Our grammar is big. We have over 1,000 syntax productions. We have over 2,000 word definitions. It's huge. And hacking on the grammar is very tricky. One person on our team is particularly, that's his area of focus, and it is not easy to hack on a grammar this big. Okay, so let's zoom in on, we want to look at why do we have these lambda expressions? How are we composing together the meaning of a bigger noun phrase? So let's zoom in on creature destroyed this way. And we're going to look at the syntax production that's combining these two branches. And we're throwing away most of the features. We're only looking at this sem feature, which is short for semantics, which we know are lambda expressions. And you see, so that's the left-hand side. Here is the first branch on the right-hand side, the second branch. And you see that we have semantics is a variable that we're reusing in the semantics of the parent. And modifier is another lambda expression variable. And we're applying them like functions, because they are lambda expressions, to each other to build this bigger semantics that then constructs a bigger and bigger logic expression as we go up the tree. So that's the most interesting variation on parsing that we do compared to what you would do with a programming language. I do want to check time. Gilbert, can I talk about an AFRA resolution? 5 minutes. OK. We're going to skip this one. We already kind of talked about it earlier. There's ambiguity. You can see that like our chart parser produces both of these trees. And we need to reject the nonsense one of destroying with flying, because that semantically doesn't make sense. We use a bunch of different techniques for ways to throw away the bad trees. But we're going to talk about a different type of ambiguity. It was that nasty word it. Something you learn in a compiler's class is that your choice of intermediate representation is very important. It determines what kind of analysis you can do. And a part of the design of AFERT is to support resolving this ambiguity. We get frames, which have slots, which correspond to nouns. And the frames are indexed, and the slots are indexed. And so we have an ordered list of nouns. And this is important for figuring out what does it refer to. And so that analysis, we do a ton of work to support how to resolve this information. So first, who can tell me in the trophy would not fit in the brown suitcase because it was too big? What does it refer to?
Yeah, like you said, the trophy.
And why?
A suitcase being too big would allow it to fit.
Right. You're using some semantic knowledge there. Some logical inference. This stuff used to be really hard for language models just like 2 years ago. Now they can do it, and it's really impressive because it's hard. So if we change one word to small, now it is instead the suitcase. But syntactically, these are the same sentence. There's just one word that's different. So there are two key rules with how to handle an AFRA resolution. An AFRA is the linguistics term for words like this, like it, that refer to earlier parts of the sentence. One is they need to be semantically compatible, the two things that refer to the same thing. And the other is that a closer referent is better. So the most recent thing you mention is probably what it refers to if they're compatible. So how do we, let's kind of walk through the algorithm we use to resolve the word it. OK, so first of all, when we do parse this, we get a semantics that it is just something of type card, which is not very helpful. We need more information about it. And we get this flag that it is false that it's resolved, and that tells the ANAFRA resolver to kick in and handle this noun phrase. So first, we look at the noun phrase one or more +1 counters, and we can do this cheap, quick check. Counters aren't cards. The type doesn't match. Yes?
Is there a reason the second part of the sentence is so wordy instead of just saying add one more?
Why it is that many +1 counters? Yeah. I don't think I can give like a good precise answer on the spot, but the answer is precision. Now the next noun phrase, a creature you control, that has the same type. It is a card. We're looking for a card. But that isn't sufficient. We need to prove not just that it's a card, but the logic expressions for it and a creature you control are compatible. And by compatible, we mean, does the logic expression of one imply the other one? So does our assumption, this first logic expression of a creature you control, logically entail our conclusion, which is this very measly, tiny expression of type card, but could be something more complex. If it's like that blue creature, that could constrain the semantics of what it is referring to further. And the way that we do this, is we call an automated theorem prover, and we give it our assumptions and our conclusion, and we ask this solver, does this logically follow? And if it does, then we're like, great, this is a candidate. And we hold on to that candidate, and we keep looking at the rest of the noun phrases. This one also doesn't match because the types are inconsistent. And we have one other noun that's hiding inside of an earlier noun phrase, which is you, the game player, which also doesn't match by type. So we don't have to do too much here. We know that it refers to a creature you control. Questions? I'm done. Yes?
So then you find a candidate, and then say you find a bunch of candidates, how do you pick a candidate?
Right, so as we're going along, we go from front to back, we find a candidate. If we find a new candidate that's consistent, one thing is we have a check that asks, is this candidate better? And if it is better than our existing candidate using a bunch of heuristics, then we take the new one, and that's the one we carry forward. And then by the time we get to the end, we have the best candidate we found that's the closest. And there's a whole bunch of heuristic logic we're using to determine that. Yes?
So this relies on like the source code or source language being relatively precise.
Yes, this is not general English, right?
But like, how diligent were they when they created those 30,000 cards? Like, I find it hard to believe that they were just really like.
Yeah.
Are you able to generalize it?
So there's this thing called oracle text. There's the printed text on the card, and then there's the oracle text, which is the canonical, current, up-to-date wording. And so they update the. So if you're playing with an older card, there's different language on there, and that's been reinterpreted as the rules have evolved over time. And so this is all based on that canonical oracle text.
And the paper game itself also has to be fully specified, and that's not even your like team's concern necessarily, right?
We need to match their specification, yeah. It's their job to specify things. It's our job to implement to the spec.
Does this always work, or do you have to have like manual exception?
So there are different kinds of manual exceptions. Sometimes the text on a card would be too much work to get to work with our grammar. And so we might substitute the text for text that is the same with maybe just things rearranged grammatically so that it works. But that's kind of our last resort. And there are a whole bunch of other types of techniques we use for things that would not be worth the effort for just one card to do it perfectly the right way. But for the most part, again, like around 80% of the cards, it works. Most of our work is not getting a card that has text we previously support, but maybe phrased differently to work. Most of our work is, there's a new game mechanic, there are new words, and we're implementing, like in a programming language that has a new keyword, we're implementing front to back how that keyword works. So that's where a lot of our work happens. Yes?
Yeah, an example of something that was really annoying to implement.
Something that was what?
Really annoying to implement.
There are, so let's see. Oh, I think we're about to be out of time. Well, okay. I can show you one thing that's an interesting example of a challenge with our grammar. We had to improve our grammar to improve the handling of this card. This has put a 3/3 colorless worm artifact creature token with Death Touch, and then another thing that's just as complex. That's tacking on a whole bunch of adjectives. And an earlier version of our grammar produced 3,000 parse trees for this because of how those all combined. And reworking the grammar got it down to 9. One more question?
Or maybe we should.
Okay, no more questions.
Let's like
Come talk to me.
Let's give Derrik another round of applause.